So the next problem in Chapter 6 is dealing with the photoelectric effect. The photoelectric effect, if you remember, is, in quantum theory, you shine a light on a metal surface, and electrons come out from the metal. Okay, so basically you have a piece of metal, shine a light like a flashlight, and at a certain intensity level, electrons are actually going to break free from the metal and come out of the metal. So these are called photons. So this next problem deals with that photoelectric effect. So a certain metal requires a photon with a minimum energy of 4.32 times 10 to the negative 19th joules to emit electrons. So the first part is, what is the minimum frequency of light necessary to emit these electrons from this metal via the photoelectric effect? So we have to think of a formula that involves energy and frequency. So what comes to mind for me is E equals HF. Okay, E being energy, H being Planck's constant, which is 6.626 times 10 to the negative 34th joule seconds. That's our constant. Okay. So that's H, and we want to solve for frequency, and we know energy. So we simply plug in the numbers. 4.32 times 10 to the negative 19th joules equals Planck's constant, 6.626 times 10 to the negative 34th joule seconds times F. So to solve for F, we simply divide by Planck's constant on each side. So divide by 6.626 times 10 to the negative 34th joule seconds. 6.626 times 10 to the negative 34th joule seconds. You notice that joules will cancel. So we're left with frequency equals, we do that on our calculator, to the negative 19th divided by 6.626 times 10 to the negative 34th, and we get a frequency of 6.52 times 10 to the 14th inverse seconds. Okay, and remember, with inverse seconds, that equals hertz, right? 1 hertz. That's the unit for frequency. That equals 1 inverse second. So that is the minimum frequency of light necessary to emit electrons. So part B asks, what is the wavelength of this light? So again, we have frequency, and we want to know wavelength. So think of some formula that involves both frequency and wavelength. So I think of C equals F lambda. And you know what C is? That's the speed of light. C equals frequency, which we already calculated, 6.52 times 10 to the 14th inverse seconds times wavelength. So again, divide by that. Okay. Okay. and the seconds will cancel. Okay. So you're going to get meters. So your delta is going to be equal to, your lambda, your wavelength, is equal to 3.0 times 10 to the 8th divided by 6.52 times 10 to the 14th. And we will get 4.60 times 10 to the -7th meters. Okay? And we can convert to nanometers because that's traditionally what wavelength is measured in. So we just convert, we multiply by, for every 1 meter, there's 10 to the 9th nanometers. So units will cancel out, and we're left with, again, just putting that into the calculator. So we we multiply by 10 to the 9th power, and we get 460 nanometers. Okay. Good. So that's the answer. That's the wavelength of this light. Okay, moving on to part C. Is it possible to eject electrons from this metal using visible light? Okay. And if so, what color light would you say? So looking back at the book here, at the Roy G. Biv, the electromagnetic spectrum, we see that 460 happens to be in the violet-blue range. So our answer is yes. It's possible to eject electrons from this. Yes, it is possible to eject electrons because 460 nanometers is within the violet-blue region. Okay. So you need to have visible light that is 460 nanometers to eject electrons. Okay, moving on to the next part. So to solve this problem, we need to find the maximum potential or maximum possible kinetic energy. So let's start by finding the energy at 235 nanometers. So that's going to equal HF. So that's going to equal, we'll break down this unit one more time to be HC over lambda. Again, I'm incorporating the speed of light equation here so that we can do this all in one fell swoop. So we will have our Planck's constant times speed of light divided by the wavelength. So 235 times 10 to the -9th meters. So bear in mind that the wavelength is given in nanometers, but we do need to use standard units. So we do need to use meters per second, joules. We do need all that good stuff and use all standard units so that our answer will be in a standard unit. So after multiplying here, just going to do that in my calculator quick. we'll divide. Okay, so we're going to get 8.46 times 10 to the negative 19th joules. So that is the energy required, or that's the energy that we'll need here with 235 nanometers. Okay, so the energy at 235 nanometers. Okay, so now we need to find the maximum possible kinetic energy. So I'm going to a new page here. Okay, going to a new page. We'll just use this for now. Okay, so again we had 8.46 times 10 to the negative 19th joules at that 235 nanometers. So the next step is to find the kinetic energy, and that will be equal to the energy at our 235 nanometers minus the minimum energy needed. So remember, the minimum energy we calculated at that 460 nanometers. Okay, so yeah, and when we look back here, that value is given here. The minimum energy, 4.32 times 10 to the negative 19. So, plugging in, we will get 8.46 times 10 to the negative 19th joules minus the minimum energy, which is given in the problem, 4.32 times 10 to the negative 19th joules. Okay, so we just subtract. So using the calculator, and we will get 4.14 times 10 to the negative 19th joules. So that is the maximum possible kinetic energy of the emitted electrons. We subtract out this minimum here, right? We subtract out the minimum because we have to get past that barrier first before we get any electrons to come out. Okay, so at 235, we take that minus the minimum because that minimum energy will be absorbed by the metal. So we need to overcome that first, and then anything left will be the energy that can be turned into kinetic energy. Okay, so the last part of the problem, so let's go to the next page here. Oh, sorry about that. Okay. So this problem work will be down here starting. What's the maximum number of electrons that can be freed by a burst of light whose total energy is 3 microjoules? Okay, so remember that 1 electron is emitted per photon. So we need to calculate the number of 235 nanometer photons in this amount of energy. The excess energy in each photon will become the kinetic energy of the electron. Okay, so here's what that looks like. Starting out, we're going to have our 3.00 microjoules. Okay, so first we convert. So in 1 microjoule, there is 10 to the negative 6th joules. Next, for every 1 photon, there's that 8.46 times 10 to the, remember this number right here, 8.46 times 10 to the negative 19 joules. For every 1 electron, there's 1 photon. Check your units, make sure they cancel, which they do. And we do all that in our calculator, so we're trying to figure out how many electrons. So we do all this out in our calculator. And we get 3.55 times 10 to the 12th electrons emitted. So this is the answer. Okay, thanks for watching. See you in the next video.